Hello guys, so welcome again to another VHDL lesson. In this lesson, we're gonna show the implementation of a 4-bit binary address. So this is a circuit. This circuit will add up three 4-bit binary numbers. Like for example, three numbers here: A 4 bits, B is another number 4 bits. C is a third number, again 4 bits. Okay, we explained this in our lecture. Please go to the specific video that explains the idea of this circuit. Okay, this circuit uses two 4-bit adders. So we add first A and B, then the sum of A and B will be added to C. Okay, each 4-bit adders here, each one of this circuit and this circuit has two carry inputs. Again, go back to the to the 4-bit other binary other implementation to see the specific details of this circuit, like the inputs and the output. So we said that any 4-bit other or the binary other that we implemented has three inputs, basically the two numbers that you're gonna add, like A and B. The third input is the carry input, and we said that this carry input should be 0. And two outputs, the sum, which is 4-bit, and a carry. Okay, this is specific circuit which will add three binary numbers together has a specific condition to be used, which is the output, which is basically which is in this case 5 bits, should be represented with 5 bits, not 6 bits, for example. So for example, if you want to add 15 plus 15 plus 15 like this, this circuit will not be applicable or not be good for you, because the output of 15 plus 15 plus 15, which is 45 in binary, is 6 bits, or needs 6 bits to be implemented. So in that case, this circuit can't be used. Okay, and we must modify this circuit, basically modify that OR here. This OR gate should be modified, or should be basically replaced with another circuit that we implemented before, and I'm gonna leave this as a homework. And in that case, it can be used to add the three others together, or I'm sorry, the three 4 bits as 4-bit binary numbers together. Okay, so there is a restriction here, is that two of these numbers, the input numbers A, B, and C, two of these should be actually 3 bits, not 4 bits. Okay, like for example, the example that we show in the lecture, like adding 15 plus 7 plus 3. Remember, 3 and 7 represented as 3, for example, is 1100, 7 is 1110. Okay, so both of them is less than 4 bits. Okay, actually 3 is 2 bits. Okay, and only the 15 that use the 4 bits, because 15 is 1111. Okay, so that's basically the circuit. So the VHDL implementation now needs to use as a module, as a a package, the 4-bit adder that we implemented before. So I created a package here for the 4-bit adder, and I called it binary adder 4-bit. Okay, it has two inputs. I called them A and B. Another input, which is the carry input, which in that case will be 0. And the two outputs, the sum, which is again 4-bit, and the carry, okay, which just one bit, of course. Okay, then of course I created this package, then added it to our digital components. Let's check our digital component here. Okay, so here it is, binary other 4 bits package, binary other 4 bits package. Okay, so it's added and it's okay now, you know. Now let's explore the design, the VHDL code for that circuit. Here is the VHDL code. So the VHDL code, the entity, we're gonna define the inputs and the outputs. So we're gonna draw like a box around, you know, this circuit here, like this box here. Okay, so what is the input for this box? You know, 3 inputs, A, B, C, A, B, C, and each one of them is 4 bits. Although in the test bench, you know, 2 of them, which basically B and C, will be only 3 bits, as we will see. Okay, the maximum will be 7. 7 is 3 bits. They will not go beyond 7, because in that case we're gonna need 6 bits in the output, not 5 bits like in that case here. Good. The output of that blue box here, 2 outputs, the sum, 4 bits again, and the carry is just 1 bit. Good. Very good. And you know, the internal implementation here needs the package of the 4-bit other. So we instantiated, or basically first we included that package from our library digital component. Okay, binary other 4 bits package.all. Good. Now the signals. Look here, there are some internal signals that we're gonna use. Basically, there are 3 internal signals. The first signal, which is the output of that guy, and the input of that guy is that signal here, which is a sum of the first stage. We can say it's the first stage. So we need, you know, I called it S1. That's fine. You can call it whatever, you know. So we need here a signal, which is 4-bit, which I call S1 here, which is the output of the first binary other, and at the same time will be the input of the second binary other, which will be added to C. And 2 carries, the carries of the first other and the carry of the second other, C1 and C2. Okay, good. Now the internal structure, which is very simple, because basically you're gonna need 1 OR gate and 2 binary others from the package that you already have. Okay, so I have here 2 instantiations, binary other 1, binary other 2. Okay, binary other 1, which is that one here, has 2 inputs, A and B. The third input, this guy here, carry in, is 0. So I put 0. That means it's a constant all the time equal to 0. And the 2 outputs, S1 and carry 1. S1 here, the signal, and C1. Good. Now the second, you know, instantiation will be for that guy here. Okay, this guy will receive as a first input S1, which is the output of the first binary other. The second input is basically the third number that we're gonna add, which is C. The third input is the carry input, that guy, which is again 0. And the 2 outputs basically. The first output is the sum of the whole circuit, which I call sum here, SUM. And the carry, you know, the second output is basically carry 2, C2. Good. Now the final step is to, you know, make the output of the carry, the final carry. And the final carry is very simple. It's basically C1 or C2. Very simple, you know, design. Again, it's a modular design, a structured design, which uses what you already have. Okay, we already did last week the 4-bit other. Then we just create a package out of it. Then after this, you know, we just instantiate and use. Good. Now the test bench. Here is a test bench. Okay. So again, as we explained before, you know, the test bench is another design, although it's like what we can say virtual design, you know. I mean, we write the test bench in a way similar to writing, you know, the a new design basically, but it's not a design, a new design. Okay, so we have the same entity, which we call component. Just copy and paste from here. Okay, then we have, you know, some signals. These signals will be, you know, we take values, you know. So we have exactly same signals as our inputs and outputs, and I called them AN, BN, CN. This will be basically connected to ABC. Sum out, which will be connected to sum. Carry out, which will be connected to carry. Then you instantiate your design here and write, you know, the signals in the same order as these guys. So ABC will be connected to AN, BN, CN. Sum will be connected to sum out. Carry will be connected to carry out. And again, review our, you know, our previous lessons to know how to write, you know, or how, you know, how you can structure or, you know, write, you know, a test bench to test your design. Okay. Now we start, you know, the process here. So as we said, these three numbers here, okay, there is a restriction or a condition to use this circuit that 2 numbers out of the 3 inputs that you have is actually less than 4 bits. Although we call it, you know, it's a, you know, a 3-4 bit binary adder, but it's not exactly like this. Okay, and again, there is a modification that you should do in this circuit, basically to replace this OR circuit with another circuit that we studied. This circuit has 2 inputs and 2 outputs. Okay, and in that case, you can have, you know, the full, you know, full definition, we can say, of this circuit, which is adding, you know, 4 bits really of three binary numbers. So the first input A will be changing from 0 to 15. So you're gonna have a counter here from 0 to 15, and this counter will be, you know, mapped to A input. So A input will change from 0 to 15. There is another counter which will be represent the B. This counter called J will change from 0 to 7. Again, 7 is 3 bits, so it's less than 4 bits. Okay. So and you will map this J to B. Finally, a third counter which would represent C. This counter again from 0 to 7. Okay, and this counter will be, you know, mapped to the input C. Then you're gonna wait for 1 nanosecond and you have the loop. Okay, so for example, in the first iteration, A will be 0, B will be 0, then C will be 0, 1, 2, 3, 4, 5, 7. Then in the second iteration, A will be 0, B will be 1, and again C will change from 0 to 7, and so on. Okay, guys, I already have the output. Okay, first, you know, to have a good view or a good understanding or a fast or a quick, you know, understanding of the output, to change, you know, the radix from binary to unsigned. So you can see at each clock here, or at each step, at each 1 nanosecond, what you are really adding. And this is very simple. I'm gonna, you know, change the color of the sum. So let's make it, you know, this color here. And this is the, you know, this is the carry output. Okay, the carry is just the 5th bit. You can say it's S0, S1, S2, S3, and the carry is like the 5th bit or S4. Okay, so look here, 0 plus 0 plus 0 is of course 0. Let's see, you know, 0 plus 0 plus 1 is 1, and of course the carry is 0. 0 plus 0 plus 2 is 2. 0 plus 0 plus 3 is 3, and so on. And since you are increasing each time by 1, the sum is going, or increasing or incrementing each 1 nanosecond with 1 again. So it's a very quick way to verify that you are really right. Then here B become 1. So A is still 0, but B become 1. So 0 plus 1 plus 0 is 1. We're going to start from 1. The sum will start from 1, not from 0. Then again, you're going to increment by 1 because basically each 1 nanosecond this is incrementing by 1. So the sum, the output should increment by 1 as well. So we're going to have a sum from 1 to 8. At 8 here, for example, A is 0, B is 1, C is 7. So 1 plus 7 plus 0 is 8, Then 0 plus 2 plus 0, it's 2, 3, 4, and so on. Let's check, some high number, because it's really interesting here when you have high numbers. Like let's check this. This is easy because it's 10 here. So 10 plus 0 plus 6. This is 16. 16 is, if you look at here, the sum is 1. I'm sorry, 0, 0, 0, 0, 1. This is 16. 4 zeros. So the sum will be 0 basically, and the carry will be 1. That's exactly the case here. The carry is 1 and the sum is 0. Then 10 plus 0 plus 7 is 17. 17 is, you have the 17 is 1, 0, 0, 0, 1. So the sum S0 will be 1, S1 will be 0, S2 will be 0, S3 will be 0, and the carry will be 1. That's exactly the case. If we, expand here the sum, look at S0. S0 is here, S0 is 1, and S1 is 0, S2 is 0, S3 is 0, then the carry is 1. Okay, guys, here is the sum. You see? So S1 is 1, I'm sorry, S0 is 1, S1 is 0, S2 is 0, S3 is 0, and the carry is 1. Let's take another, interesting, like this one here. Still A is 10. Now B is 1. So 10 plus 1 is 11. 11 plus 7 is 18. 18 is 16 plus 2, or 18, right? So 16, we know that 16, any number 16 or above, the carry should be 1, because the carry is the 5th bit 2 to the power of 4, which is 16. So the sum should be 0, 1, 0, 0. So S1 should be 1, S0 should be 0, S2 will be 0, S3 will be 0. Let's check that. So S0 is 0, S1 is 1, S2 is 0, S3 is 0, as we said, and the carry is 1. That's 18. 16 plus 2. 16 is the carry, and the 2 is S1 here. Okay? Let's take, another high value. Let's check the 15, So let's start by 15 here. So 15 plus 0 plus 0 is 15. 15 is 4 ones. And of course, the carry is 0. So 15 is 1, 1, 1, 1, and the carry is 0. That's exactly the case. Look, S0 is 1, S1 is 1, S2 is 1, S3 is 1, and the carry is 0. Now, 15 plus 0 plus 1 is 16. 16 is again 16, which is in binary. Will be 0, 0, 0, 0. So the sum will be 0 and the carry is 1. So all the sum bits here are zeros. Look, and the carry is 1. Okay, let's take, another high value like, 15 plus 7 plus 7, for example, as the last one. Yeah, it's in here. So 15 plus 7 is 22. 22 plus 7 is 29. 29 is actually 16 plus 13. Okay, 16 plus 13 is 29. So the carry will be 1, which is 16, and the sum should be 13. The sum is 13. Look, the sum is 13 here. 13 is basically 1, 0, 1, 1. I mean, S0 is 1, S1 is 0, S2 is 1, S3 is 1. That's exactly the case. S0 is 1, S1 is 0, S2 is 1, S3 is 0. That's the 13. And the carry represent, the 16. So 16 plus 13 is 29. Okay, guys, that was basically, you know, the 4-bit binary number adder, binary adder. Okay, and again, this, there is a restriction for this circuit. This circuit can add numbers that will result in 5-bit result. If your result is 6-bit, like or need 6 bits, like for example, adding 15 plus 15 plus 15, then you need to change this OR here. This OR should be replaced by a circuit that we studied before. This circuit can take 2 inputs, 2 bits as input, like carry 1 and carry 2 in that case, and the output will be 2 bits as well. Okay, so, and in that case, you're gonna have 4 bits from the sum and 2 bits from this circuit, and this overall will be 6 bits. Okay, and in that case, you're gonna see that, you know, yes, 15 plus 15 plus 15 will be equal to 45. Okay, but you can't do that with the current version of the circuit with the OR gate here. Okay, guys, thank you very much for watching, and see you in the next video. Bye-bye.